We are here to help.
In this video, we are going to learn how to use the method of variation of parameters to solve non-homogeneous second-order linear differential equations. First, let's go over the idea of how the method of variation of parameters works. Consider a linear second-order non-homogeneous differential equation and its homogeneous solution h of x. To find a particular solution, we will be finding two functions u1 and u2 such that u1 times h1 plus u2 times h2 is our particular solution. As we can see, the method of variation of parameters relies on finding the homogeneous solution first. To solve for these two functions u1 and u2, we use the following two formulas. When f of x is the non-homogeneous part of the original differential equation, a2 is the coefficient of y double prime, w of x is the Wronskian of the homogeneous solution, w1 of x is the Wronskian with the first column as 0, 1, and w2 of x is the Wronskian with the second column as 0, 1. These two formulas are not too difficult to derive, but we will not be showing the derivation in this video. Plugging u1 and u2 into the equation for p of x, we obtain the following equation, where c and k are constants of integration. If we simplify this equation by taking c and k out of the brackets, then take these terms to the end, we observe that this is exactly the homogeneous solution with c1 equals to c and c2 equals k. If we were to plug p of x into the differential equation, ch1 plus kh2 would end up simplifying out to be 0, since it is the homogeneous solution. Therefore, ch1 plus kh2 doesn't add anything to the particular solution, so we can assume that the constants of integration c and k equal 0. Let's look at an example. Consider the following second-order differential equation. As we can see, the coefficients are all constant, and our non-homogeneous term f of t is e to the t over t squared plus 1. First, we solve the corresponding homogeneous differential equation. Solving the characteristic equation, we find that m equals 1. Since we have repeated real roots, our homogeneous solution is h of t equals c1 e to the t plus c2 t e to the t. Before we solve for our unknown functions u1 and u2, we need to calculate the Wronskians. In this example, the Wronskian in the denominator is e to the power of 2t. Before we solve for u1, we need w1, which will be negative t times e to the t, and a2, which is 1. Plugging everything into the formula for u1, we get the following equation, which simplifies down to an integral we can solve using substitution. We will leave the substitution to the viewer to verify that the solution for u1 is negative 1/2 ln of t squared plus 1. Solving for u2, we first need to calculate w2, which is e to the t. Plugging everything into the formula, this simplifies down to an integral that can be solved using trig substitution. We will leave the integral up to the viewer to verify that the solution for u2 is tan inverse of t. Putting this all together, we have our particular solution p of t, and therefore the solution to the differential equation is the sum of the homogeneous and particular solution. To summarize, we can use the method of variation of parameters to solve non-homogeneous second-order or higher-order linear differential equations, as long as we can solve for the homogeneous solution. If the homogeneous solution cannot be obtained, we can't use this method. Solving for the two unknowns, u1 and u2, involves solving two integrals. Variation of parameters may become challenging if these integrals cannot be solved by hand. Thank you for watching. We're here to help.